This one is really straightforward. We have to compute work, which is force times distance. But the only force in this is going to be friction, which if you work it out is about 50 newtons. So the work is just going to be the 50 newtons of friction times 6 meters equals 300 joules, not newtons. Did I do that to trick you, or did I do that because I made an honest mistake? I'll let you judge. Now we have a torque wrench, 296 newton meters on a 0.3 meter wrench. What force has been applied to the wrench? Well, torque is force times distance. We need to solve for force. So force is torque over distance, which will be 986 newtons. That's how much force you're going to need to produce that torque on that radius of turn. Any mass we can pretend is in a gravitational field, so we can turn newtons to their equivalent in kilograms if it was a dead weight. And this comes out to about 100 kilograms. That, unfortunately, is my weight. I'm working on it. It should be more like 70 kilograms. Got a 7-year-old child to lose in dieting. So this is the weight of a full-grown man. It's doable, but it's going to be quite a pull for some people. This weightlifter holds something over his head. The force. Wrong units. One is down. You're going to do MGH. So we're getting roughly 4,000 newtons. If you did 400 times, what did I do here? Yeah, 400 times 10. All right, you could do it in your head. I had a brain catch for a moment. This one, you're just adding up these two forces. You want to get crazy, make positive to the right, negative to the left, you add them all up. But plain logic, it's 100 newtons to the left, and my stupid yellow box decided to move itself over there. So yeah, that's the wrong spot. And then it did this today. Worked fine at home, not here. We put like 12,000 newtons of force on this elevator. So 12,000 newtons going up, and we have 94,000 going down. It leaves us with an acceleration of 8.55 meters per second squared down. I do not recommend going on this elevator. It's not quite free falling, but it's moving. They kind of should have made a tighter cable. You just have slightly longer to fall to your death than if it was just cut. Now, why did I do an exact calculation here and no rounding? Well, I still rounded a little bit, but these numbers are too close together, right? I chose these. When you see that, you go, uh-oh, I better use my calculator. They're too close for a ballpark guess. These ones. Normal force is a contact force. Okay? No. It just disappears. Now, there's some false grammar in this question. If you read it through, it kind of can actually let you choose any of them. All of these are false about frictional force, except it opposes motion. Mass is important. The surface material, the friction coefficient isn't unique. It depends on two materials, and there's bazillions of combinations. Some will overlap. And it doesn't have to stop an object, right? You could be sliding on the ice and hit a rough patch, and for a moment you're slowing down. But no, it will slow an object down, but whether it brings it to a dead halt is not really relevant. This guy, you work out what the energy necessary is, a real simple calculation. Now, if you look at my choices, two of those weren't even in the running. They were the wrong units. In your head, if you do 73 times 2 is 146, times it by 10 is about 1,400. Those are your only two numerical answers left. So really quick in my head, 730 times 2 is 1400. It's that one. This one. The torque on the load arm is 3,600 newtons a meter. That must also be the torque on the effort arm. So the torque on the effort side must equal this number here. So our mass, okay, is force divided by 9. I've got a typo here, which gives us a force of 400 newtons. Okay, so there's a typo here. There should be a division sign. But you didn't have to do that. That's the answer. But look, if all you've done is take the boom arm and make it 3 times longer, the force necessary would drop by 3. You could have skirted this question in a split second by thinking about what you're being asked. Now the van one has an interesting problem with it. All you have to do is see the van for what it is. That wheel is a lever. He's pushing down with 600 newtons force. You take that 600 newtons and multiply it by this length, you've got your torque of 138 newton meters, which the engine can easily overpower. The engine's going to win. The trick is this distance here. I gave you the rim diameter, didn't give you the rim radius, but the picture shows a radius being marked. So some of you would get an answer of 276, exactly double. You were correct. When you get 2 times or half size, I guarantee you can find that error. If it's a multiple of 2 from the book answer, you have made an error that's nearly correct. No errors are necessarily random. There's a pattern to your error. Go looking for it. You'll find the solution. Force on this spring is from the weight hanging off of it. It's 3 newtons. The force on a spring is Kx. We want to find X. We do this. We get 0.18 centimeters. That's good because I rounded here. These parents, the energy in their arrow they've given the kid, K of 5 newtons per centimeter. 0.5 is the half. 30 centimeters squared. Centimeters. I get 2,250 joules. That energy is going to go into height. So if we solve for height, it's going to be energy over mg. We do this, and we get 11,250 meters. Whoa. That's 11 kilometers straight up. What the frickin' kind of bow did they give the kid? Well, look at my elastic coefficient. 5 newtons per centimeter and a 30 centimeter draw. This bow is going to have 150 newtons pull. That's 15 kilograms or 33 pounds of draw, and you've only pulled it out a foot. Like less than the length from your wrist to your elbow is how much you drew that, and you put 33 pounds of force into it. That arrow is going to come off like a bat out of hell at 20 grams. Is it going to reach 11 kilometers? Hell no. With all the air resistance, birds, a plane, that arrow has no chance of reaching 11 kilometers. But on the moon, it's within theoretical possibility. If you had a really good hunting arrow, you could start taking pot shots at spaceships with it. Not on Earth. Too much air. And I'm done.